Good morning to you all. So welcome back. Yeah. So I thought in a bit different way. So first, let me try to finish it up. The another part of the pile foundation, that is the pile group. The theory part, the design or not design, the pile load calculation capacity. So let me discuss for about maybe 45 minutes or 1 hour. So it will be completed, and thereafter I can further go on the tutorial in the evening time also, 5 to 6:30. So I can cover the tutorial. If you recall, in the last class we were discussing, I have been introducing about the pile group. So in general, construction of a single pile is very rare situation. In most of the situations, we normally go for the pile group. So we also did discuss about the pile group. So when you talk about the pile groups, so these are again slender structural element. However, more than one number of piles are integrated. So with another structural element that is called as a pile cap, as is seen in this picture. Now we also did discuss, so when all these piles are integrated with the help of a pile cap, now this pile cap may be or may not be in contact with the ground surface. So depending upon the pile cap in touch with the ground, so then you need to assess the pile capacity, so especially frictional capacity for the entire length of the pile, or only up to that length which is embedded within the soil sample or within the soil mass. So these are the two variety of piles, where in the first case the
Sir,
pile, yeah.
So you are not sharing your screen.
So this is the first case where the pile cap is in touch with the ground surface. So this is the second case where this kind of situations we can see, especially on the river beds, where the sufficiently above the ground surface, and often there is an flow of water. So a part of the pile which is above the ground surface may be below the water, and part of the water exposed to atmospheric condition, as you can see from this slide. So the above two pictures are the cross sections of a pile group. While if you look at the plan, so this is how the pile groups looks like. So here, if you look at carefully, there are 9 number of piles are arranged in a square pattern. So this arrangement is called as a 3 by 3 number of pile groups. Now, based on the all previous classes, we were knowing the geometry of the pile, that is pile diameter and pile length. Now, when you talk about the pile group, some additional geometrical parameters comes into the picture. Among them, one of the most important parameters is the spacing between piles. So that is represented with the D. So D is most crucial. So the spacing between the piles is the critical impacting factor of the pile group efficiency. And so this is the further geometrical parameters of the pile group include length of the pile, that is LZ, and width of the pile group, that is BZ. D is the spacing between the pile group. Now we also did discuss about how to calculate the length of the pile group and width of the pile group. Suppose if you presume that n1 number of piles are there in the length direction and n2 number of piles are there in the width direction. the total length of the pile group Lg is nothing but N1 minus 1 into D plus, since the D is always measured from center to center of the pile, so the half the pile diameter on one side and another half from the other side will be added, that is 2 times of D by 2. Similarly, in the width direction, uh, N2 minus 1 into D effectively nothing but the number of spacings. Suppose here if you look at the LG with length direction N1, that is number of piles. Here the total number of piles are 3, but the number of spacings are 2 only. So 3 minus 1 will give you 2D, that is 2 number of spacings multiplied by, since we are measuring center to center distance, that is D, so half the pile diameter on the left side and half the pile diameter on the right side, so will become additional. So therefore total length of the pile group is N1 minus 1 into D plus D, capital D, or 2 times of half the diameter, anything is okay. Then these are the possible pile group geometries. A pile group may contain 2, 3, 4, 5, 6 or any number. We can go up to 16, 25. Then we also try to understand how the load distribution takes place when you use the shallow foundation or a single pile or a pile group. So here if you look at the up right side picture, the left side picture represents that of a shallow foundation. So this is how the load distribution happens below the foundation. That is typically represented with the help of the pressure bulb. While the same pressure bulb can also be drawn for the pile group. So if you draw the pressure bulb, that somehow looks like. While when we discussed about the shallow foundation, so we have approximated that the pressure bulb extends to a depth of equal to approximately B or 1.5 times of B. Similarly, in case of the pile group also, the pressure bulb might extend approximately to a depth below the pile tip up to B, where B is the width of the pile group, pile cap. And the above picture represents the load distribution, while below picture represents the stress increment at the pile tip of single pile as well as the pile group. Now, if you try to interpret all these diagrams carefully, one thing is clear that when you go for the pile group, so where there are more than 2 number of piles or more than 1 number of piles, so these group could able to resist more amount of the stress of coming from the superstructure load. So that's what we could able to infer from all these diagrams. This is the load distribution again in case of the sand. So then we also try to understand some more information about the pile group efficiency in the driven pile, especially if the driven piles are used in cohesionless soil, that is the sand. The driving force accentuates or the densifies the surrounding soil of the pile foundation. So as the density increases from the pre-driving to the post-driving, so there is a consequent improvement in the frictional angle. So therefore, the pile group efficiency may be higher than the pile capacity, that is summation of all the piles. And we also did discuss about negative skin friction that can arise when there is a compressible soil, especially clay. Now, how to distinguish between negative skin friction and positive skin friction? Positive skin friction means whatever the skin friction, we did discuss about the skin friction calculation of the individual file. While negative skin friction means this especially arises in clay type of the soil, because during the pile driving or after the pile driving, when the superstructure load gets transmitted to the surrounding soil in the form of a skin friction. So this, say for example here, so here this is a clay layer. So when the load is getting distributed or transferred from the pile, so this layer, instead of offering the resistance, that resistance as is shown in the case of the sandy soil as an upward arrow, but this clay layer undergoes compression. So thereby the resistance is shown in the form of a downward arrow. The downward arrow indicates that the friction is developing. However, that is not accounted for load resistance. Rather, this negative skin friction becomes additional load. In fact, the negative skin friction becomes additional load. That's why wherever, if you are assuming that the clay layer present, first of all you have to inherently take negative skin friction. So not everywhere, wherever there are the compressible clay layers exist. So don't take it this as an in general case of developing the negative skin friction. So if that is the case, whatever the theories that we have discussed, alpha, beta, lambda, so they are not valid. Okay, so don't take in general. Only in case of compressible clay layer only there is possibility of the development of the negative skin friction. So if you refer to any book, if you see that the arrows are represented in the downward direction for a particular clay layer, then you have to inherently assume that this is nothing but the negative skin friction, not the positive skin friction. So this is the pile group. Now one important point that you need to understand is how the stress gets developed between the or within the soil when you use the pile group. So for example, for the sake of illustration, there are two piles and a 4-pile group has been taken here. So let us look at the above diagram first. So here this is individual pile number 1 and individual pile number 2. So if you draw the approximate pressure bulb diagrams, so this is how they look like. But if you look the soil which is between the two piles, now this pressure bulb indicates that this is the volume of the soil that experiences the load coming from the superstructure or pile. Now, but the soil in between the two piles where the overlap of the pressure bulb can be seen here. So what is the meaning of this one? The meaning of this one is, so here in this area the soil is experiencing load only from the pile number 2. Similarly here also this indicates that this soil is experiencing the load coming from the pile number 1. Wherever there is an overlap, it indicates that this small volume of the soil experiences the load coming from both pile 1 and pile 2. So meaning thereby, if this volume fraction is relatively high, so you can see a kind of difference in settlement, because this small overlap zone undergoes more amount of the settlement because the stress is coming from pile 1 and pile 2. While in other zone, the soil experiences the load exclusively either from the 1 or 2. So therefore, when you design any pile group, ensure that there is a least amount of the overlap exists between the piles. That's all. So now, how do you overcome this limitation? That limitation is overcome by optimizing the spacing between the piles. That is D. That's what I told. D is the most critical parameter in case of the pile group. If D is so small, then one can easily anticipate more volume of the overlap. More overlap means more stress is going onto that particular soil. More stress means more settlement, which is not advisable. And moreover, if you look at, say for example, if you look at zone 1 and zones 2, in the zone 1, the stress is coming from the pile number 1 and pile number 2. So in the zone 2, the stress is coming either from the 1 or from the 2. Now you can also anticipate some kind of differential settlement between zone 1 and zone 2, and which is also not advisable. So that as we understood from the shallow foundation, differential settlements are the most dangerous. So for any foundation, say whether it is a pile foundation or the shallow foundation. So to the maximum possible extent, when you design any foundation, I always try to avoid the occurrence of the differential settlement. or you design the foundation such that the differential settlements are minimal, such that the structure is safe and the no other possible deviations are possible in the design. Now typically the spacing between the piles are taken as 2.5 times of D in practice, or otherwise you can go for 3 to 3.5 D in ordinary situations. Now there are a lot of guidelines are also provided by different codes or standards. You can refer to any of the code or standard to pick up what particular value of the spacing depending upon the soil type, depending upon the pile type, number of piles, so on and so forth. Now another illustration that can be made from this figure is, let us look at this 4 pile group. Now here the central small circle indicate this is a pile, while this outer circle indicates the zone of influence are nothing but your pressure bulb. Now if you look at carefully, there are 3 or 4 specific zones that can be seen. For example, zone 1. In this zone 1, this soil experiences load only from this pile. The zone 2. So in zone 2, the load is coming from 2 piles on left and right side. And another is zone 3. Zone 3. If you look at the zone 3 experiences the load from 3 piles, while the last one is the zone 4. Zone 4. In zone 4, the soil experiences the load from all the 4 piles. Okay. Now, what is the takeaway from this illustrative diagram? So it is advised strongly to minimize zone 3 and zone 4 to the least possible volume, so that the load coming from the 4 piles on zone 4 will be least and it won't undergo excess settlement. This is the most important, which otherwise the central portion, just imagine, the central portion undergoes more volume of settlement as compared with the peripheral soil. Say if this is the central portion of the soil and this is the peripheral soil, so the central portion of the soil undergoes more amount of the settlement as compared with the outer peripheral soil, and which is more dangerous and it is not advisable. It's not advisable. This is how.
Sir,
Yeah.
sir, here the soil is settling, but not the foundation, sir. Why the problem will arise?
See, once the soil is settling means there is a separation of the particles. There is a separation of the particles. Suppose say if the settlement is say exceeds 10 millimeter, how the soil accommodates? To accommodate that settlement, the gap has to form within the soil sample. Okay, when it is settling, the obviously gap will form. So once a gap is formed, that has a negative impact on the overall foundation system. Okay, so that is the reason we should avoid the differential settlements.
Sir, this means density is decreasing. That is the reason.
Nothing to do with the density. In fact, the soil will be compacted now. See, for example, if you take the zone 4, the load is coming from all the 4 number of piles. So more stress means more compaction or more densification. More densification means more volume change. Did you understand? Still there is a question.
Sir, like if this goes down, then another soil means the soil which is above will come down. Like it will fill the gap.
Okay, let us take here another. Okay, see for example, here in this zone, the soil, say I'm taking zone A and zone B and zone C. So as you rightly said, suppose if the soil in the zone undergoes compression, there is an overburden right above the zone A, which is coming from the zone C. Okay, and when the zone A undergoes the compression, this overburden also try to come down. This overburden soil also try to come down. or move along with the zone 1. So this is that integrity problem. Default they will come. Now how long this movement will take place? Until there is a contrast in the material. For example, that contrast is possible between pile cap and the soil. Suppose here. So the above is the pile cap, below is the soil. So this zone C, right from the below the pile tip, it will try to again settle as a result of the settlement of the zone A. Means within the due course of time, you can see a gap formation between the pile cap and the soil. Pile cap and the soil. Now, when you have designed the pile group, so this gap formation has not been accounted for. Now, as a result, so the amount of the friction that should obviously get developed along the pile periphery might not be developing. Because here, say for example, this zone you have accounted initially for the pile capacity. But because of the formation of this cavity, so this might not be contributing in the due course of time. So that means this has an impact overall on the superstructure. So this is how it gets impacted. Is it okay?
Yes, sir. Yes, sir.
Okay. So this is the obvious impact of the despacing. So in order to avoid the excess stress on the soil, so we should optimize the spacing between the piles. And the efficiency generally represented with eta. So eta is defined as the pile group capacity of whole pile group divided by the pile capacity of individual pile multiplied with the number of piles. That is summation of all the piles. So when I talk about the pile group efficiency eta, so there are two things that comes into the picture or for the calculation purpose. One thing is the entire pile group as an independent system, or the summation of the number of piles multiplied by pile capacity of the individual pile. So these are the two things that will come into the picture when you deal with the pile group. Now let us try to understand the same aspect a little bit further details. Now depending upon the spacing within the group, the people have found that the piles may act as a block with single dimension. As a block means the block having a length of LZ and width of BZ. That is called as a block. Or as individual pile means the any single circle. So here there are 9 individual piles are there. So the individual piles means 9 multiplied by the pile group capacity, that is individual pile group pile capacity. As a block means the entire LZ by BZ acting as a single pile. That's what is the meaning of a block. Okay, I repeat again. Depending upon the pile spacing, that is D, depending upon the spacing, the pile group may act in two different modes. The first mode is it will act as a block where the LZ by BZ will act as a single pile. In that case, when I say block, pile as well as the soil within these or between these 9 number of piles will act as a single monolithic structure. That's what is the meaning of a block. Okay. Individual pile means single pile multiplied by number of piles. In case of the block comprises of 9 number of piles as well as soil between these piles. So together acts as a block or integrated element having a geometry of LZ by BZ. I think this is a simple understanding about the block and individual file. So when you try to do tutorial, then you can more understand what is the meaning of the block or how to determine the file capacity considering the block and individual file. Anyhow, we have dealt with already. So the second is another big problem. Now the first one you need to understand. So if the piles act as a block, the friction capacity is determined as F average into Pg into L. Now let us try to compare this with the individual pile. Now here F average is unit skin friction. This is very similar to the individual pile. However, when you calculate the F average, so there you have taken only the individual pile in the previous class. But in the pile group, it is something like the block. Now let us also see the perimeter. So in individual pile, the perimeter is simply taken as pi multiplied by d. This is if the pile is circular. But the same circular pile is used in the pile group. But the perimeter is nothing but cross section of the block. That is 2 times of LZ plus BZ. That's it. 2 times of LZ plus BZ. The perimeter of the square. Okay, and F average, how to calculate the unit skin friction, I will explain in the subsequent slides. So for each pile acting as an individual pile, the ultimate capacity is nothing but P into L into F average. So F average is unit skin friction, but here the perimeter is pi times of D. In the pile group, the perimeter is 2 times of BZ plus 2 times of LZ. But in case of the individual pile, perimeter is pi into D. So as we are talking about the pile group comprises of 2 components. One is as a block. So this is a block. As a block. Then this is summation of individual piles. This is summation of individual pile. So then let us try to understand how the despacing impacts the overall efficiency. So pile group, as we have seen from the previous slide, the skin friction is nothing but F average into perimeter into length. So the perimeter is written in terms of the number of piles or spacing. While that is just to make you understand more. So let's see here, the perimeter of the block is 2 times of here N1 and N2. N1 number of piles in the length direction, that is 1, 2, 3 here, and N2 number of piles in the width direction, again 1, 2, 3. Minus 2 means if you look at the previous slide here, okay, here it is given LZ means if you substitute LZ plus BZ, these equations, and these two here N1 and N2, then if you simplify, then what you get is PZ, perimeter, the same equation. See, this minus 1 plus minus 1, that is minus 2. So N1 plus N2 multiplied by D plus 4 times of D here. 2 times of D plus D. For here all the 4 corners will come into the picture. So therefore we take 4 times of the pile diameter. Now substitute the same thing here. So F average into, this is nothing but the perimeter. So this is the inside bracket represents the perimeter of the pile group multiplied by the overall length of the pile divided by the skin friction of the individual pile. So here N1 number of piles in length direction, N2 number of piles in width direction. P is perimeter of individual pile. L is the length of the pile. F average is unit skin friction. Now the length of the pile is remained same whether it is a pile group or individual pile, because individual summation of individual piles are the pile group. So therefore there should not be any change in the pile length. So the pile length is remains same whether it is a pile group or individual pile, and the unit skin friction also we can assume similar whether it because the soil is remained same. So therefore F average will be remained same in case of the pile group or the individual pile, and the remaining is the perimeter of the pile group divided by the perimeter of the individual piles. So this is how the simplification you can do it. Now here if you look at effectively, it shows or demonstrates that your pile group efficiency is a strong function of the pile spacing, strong function of the spacing between two piles. So that's what we can interpret from this simplification. So then the same thing can be written here. Suppose if you take this simplification, that is eta as this equation, then you can rewrite as Q Gu is equals to the eta multiplied by summation of the ultimate bearing capacity of the individual pile. Now depending upon the value of this eta, the pile group capacity can be said as greater than 1 or less than 1. So if the center to center spacing D is large enough, that is D is large enough, then the efficiency can be greater than 1. In that case, the piles will behave as individual piles. Thus in practice, if eta less than 1, then the pile group efficiency is nothing but the summation of all the piles. If eta is less than 1, then eta multiplied by the pile capacity of individual pile multiplied by the summation. Okay, and if eta greater than or equal to 1, then pile group capacity is summation of all the piles. If eta greater than or equal to 1, the pile group capacity is nothing but individual pile multiplied by the number of piles. If efficiency is less than 1, then that efficiency should be multiplied with the pile capacity of individual piles multiplied with the number of piles. So here there are some information about what is the efficiency of the despacing in case of the clay, as you can see. So this is a graphical representation of despacing effect on the pile capacity. So in case of the clay, here efficiency value they have given 0.5. Suppose in case of the clay, if you take the pile spacing as 2 times of D, the efficiency is less than 1, and if you increase the D spacing, there is an increase in the efficiency also, but after some time it is becoming almost constant. So similarly in case of the sand, so this is what happens. In case of the clay, as you have increased the D spacing, the efficiency increased. But in case of the sand, as you are increasing the spacing, the pile group efficiency decreased. So this is the difference between the behavior of the sand and behavior of the clay in pile group. Again I repeat, in case of the clay, as increase the spacing, there is an increase in the pile group efficiency. In case of the sand, as increase the pile spacing, the efficiency got decreased. So let us come to calculation of the pile group capacity. So here it is elaborated in terms of the steps. Now as I told, when you try to calculate the pile group capacity, again we need to assume so whether the piles are embedded in sand or embedded in clayey soil. So first I am taking the case of ultimate capacity of the group piles in saturated clay. Step 1, determine the pile capacity of the individual pile. So that is again when you talk about the individual pile, so it is nothing but the point bearing capacity plus skin friction and multiplied by N1 and N2, number of piles in length direction and number of piles in the width direction. So now for example here if we take this diagram, so this is not a square pattern, rather this is a rectangular pattern. Now here if you look at In the width direction, there are 3 number of piles, but in the length direction, there are 5 number of piles. That means N1 can be taken as a 5 and N2 can be taken as 3 or vice versa. It is up to you. You are free to choose whatever it is. Okay, so then QP is the point bearing resistance. QP is nothing but CNC into AP, because you are talking about the load, capital Q. So AP, that is cross sectional area of the individual pile, multiplied by NC, that is bearing capacity factor, NC, multiplied by CUP, that is undrained cohesion of the clay at pile T. Undrained cohesion at pile T, because this is the soil that is bearing the point load, or the soil below the pile tip experiences the load coming from the piles. Therefore, strictly you must consider cohesion of the soil right beneath the pile tip, not even above the pile tip, right beneath the pile tip. Similarly, how do you determine the skin friction? You can use either alpha method or beta method or lambda method. So if you are using the alpha method, then QS is nothing but summation of alpha into P into Cu into delta L. So alpha is adhesion factor, P is the perimeter, Cu is undrained cohesion, delta L is length of the particular soil strata or soil area. Now if you substitute QP and QS in the above equation, then the ultimate pile group capacity of the individual piles can be written as N1 multiplied by N2 multiplied by QP, that is 9AP into Cu plus QS, that is summation of alpha P into Cu into delta L. Now let us try to have a comparison. So if you compare the pile capacity of the individual pile and in the pile group, the equation is remained same. Just recall, the equation is remained same. The only difference is the pile capacity of the individual pile is further multiplied with the number of piles in the length direction and number of piles in the width direction. Number of piles in the width direction. So this is one way of determining the pile group capacity. Now the second is determine the ultimate capacity by assuming that the piles in the group act as a block. So in the previous slide, here we have determined the pile capacity of individual pile capacity of the individual pile. In step 2, consider the pile group acts like a block, Now here block means the dimension of the block is LG, that is length, by BZ, and the total length of the pile is remains same. So LG by BZ by L. And in this case, suppose if you are assuming the pile group as a block. Again, I repeat, when you say it is a block, this block includes number of piles as well as the soil. Everything will integrate themselves and act as a monolithic block. So the skin resistance of the block is determined as summation of Pg into Cu into delta L. Now here the Pg means perimeter. Perimeter can be written as 2 times of Lg plus Bg, because this is a rectangular section, multiplied by Cu and multiplied by the delta L. So depending upon the number of layers, you can keep on adding the same thing. And similarly, in case of the point bearing capacity of the pile group, so this is the equation. The equation is very similar to the individual pile with a small change. The form of the equation is remains same, that is CNC into AP. CNC into AP, where since you are dealing with the point bearing capacity, again you should not forget the cohesion shall be taken of the soil below the pile tip, not even above the pile tip, below the pile tip. And NC star is bearing capacity factor. So the value of NC star shall be picked up from this predefined graph. So here a graph is developed between NC star versus, this is what is this? Let me show the x-axis. So this is NC star versus this is NC star. So this is the graph. 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 So The x-axis is L by BG, L by BG, NC star versus L by BG, and the third parameter is LG by BG, LG by BG. Now we may deal with variety of the piles, square, rectangle. So LG by BG 1 represents the square, that is number of piles in the length direction are equal to number of piles in the width direction. Or it could be rectangle like LG by BG greater than 1, that is 2, 3 and infinity. So using the chart, one can able to pick up the value of the NC star. And how do you determine the skin friction? So this is point by this. Now if you put summation of QP plus QS, the pile capacity of a group as a block is nothing but LG BG CU into NC star, CU into NC star plus summation of the 2 times of LG plus BG into CU plus delta L. So the first term is the point bearing resistance, Now see the another difference. In case of the individual pile, AP is nothing but pi by 4 into D square. But in case of the pile group, the cross section area is nothing but LG by BG, because this is acting like a block. So the block could be square or rectangle, doesn't matter. So but always the AP cross section area of the pile group block is LG by BG only, LG by BG. So this is a point bearing capacity, while the second term is skin friction. Okay, so compare the values obtained from step 1 and step 2. The lower of the two values is regarded as the pile group capacity. If anybody has any question, please ask me. If you have any difficulty in understanding the pile group capacity by considering as an individual pile or considering as a block. Any questions? Any questions? Okay, so that is one aspect of the pile group. The another aspect of the pile group is how to determine the settlement, because since beginning of the foundation engineering, I was keep on insisting about two important things. If a foundation may fail because of the excess stress inducement, or alternatively, if the settlement exceeds certain value, then the foundation may fail or may become not functional. So therefore, it is mandatory to verify for both stress condition as well as the settlement. So then in case of the pile group, how do you determine the settlement? Again, we should think of two variety of the soils. If the pile group is installed in sand, how do you determine the pile settlement? If the pile is installed in the clay, then how do you determine the pile? So so these are the equations, settlement of pile group. So this is the equation proposed by Vesic in the year 1969. So SG is nothing but square root of BG by D into SE. So here SG is the settlement of the pile group, elastic settlement of the pile group. Then BG means that is width of the pile section, that is group pile, and D is width or diameter of the pile, and SE is elastic settlement of the each pile at comparable working load. Now how do you determine the same pile group efficiency, settlement, elastic settlement, using the in situ techniques like SPT value. So people have given n number of equations. If you refer to any of the foundation engineering book, you will get plenty of variety of equations Some may be relating settlement with the institute technique like SPT, RCPT, RSCPT, DCPT, etc. etc. So don't get confused. You can use any of the equation. However, you have to look for the validity of such equations. So for example, Visick has proposed this equation and Meyerhoff has given this empirical equation. Meyerhoff has related with the elastic settlement of the pile group with the SPT value. So then consolidation settlement of the pile group. So once we understand about how to calculate elastic settlement, so then the next step is, if the pile group is installed in the clay, then how do you determine the consolidation settlement? So the procedure I'm going to explain is somewhat very similar to the consolidation settlement that we did discuss during the shallow foundation. However, there are some specific points are there, so that you need to understand in case of the deep foundation. Say for example here, this is the pile group. So this is the pile group. Say for example, this is acting as a block, where the length of the block is LZ and the width of the block is BZ. Now, how do you determine at any given depth the increment in the stress? You remember, suppose say this is the pile group as a block. So this is pile cap and this is pile group as a block. Now this says that suppose say this is how we assumed in case of the shallow foundation as a load distribution. The same can be valid here. It is 1 horizontal to 2 vertical or something, whatever. Yeah, there are 2:1 lines, 1 horizontal or 2 vertical or 2 horizontal 1 vertical. So 2:1 load distribution. Now suppose say at this point, how do you determine the increase in stress? That is delta sigma dash. How do you determine the delta sigma? So the load is Q, the total pile capacity is QG, Now how much amount of this QG shall be considered at any given depth in case of the consolidation settlement? So this is very simple. The total load divided by the cross-sectional area. So here the cross-sectional area in one direction is, so this is BZ plus Z. Z means the depth from the pile tip to the corresponding layer. And similarly on the other direction, so that will become your so LG plus Z. So this BZ plus Z and LZ plus Z we understood when we have dealt the shallow foundation consolidation settlement. So the same philosophy is valid true in case of the pile group as well for calculating the pile consolidation. Okay, so that's why the increase in stress at any depth below the pile tip is nothing but total pile group load divided by the cross-sectional area. Okay, I hope this point is clear to everyone. So there is nothing new. But one important aspect about the pile group consolidation settlement is in case of the shallow foundation, that is there, I can explain. Yeah. Now let us look at. So this explains about how to calculate the consolidation settlement. Now here, suppose you take this is QG is the total pile load. Now one important point that everyone must remember when you go for consolidation calculation settlement in the pile group, say if L is the total length of the pile, now you need to assume something called as a fictitious footing, that is the reference line A and B, you need to assume this one. So but at what depth you will assume this fictitious plane AB? That should be assumed at a depth of 2/3 of L from the pile cap, bottom of the pile cap. 2/3 of L from the bottom of the pile cap. Now, from the Pictidius plane of AB, you need to assume the load distribution that is spreading with a dispersion of 2 vertical to 1 horizontal. 2 vertical to 1 horizontal, as is shown here. Now, depending upon your interest, suppose say you want to determine the settlement at the middle of the clay layer. So here you need to determine again the increase in delta sigma. Increase in delta sigma. So again you need to draw an horizontal line. So on this you need to determine the delta sigma. So from the Pictidius plane, until the middle of the clay layer will become the Z. Okay, will become the Z. Now, just for your understanding, here it is been given for layer 2. So this is clay layer 1, clay layer 2. So clay layer 2, Zi is nothing but L1 by 2. So Zi is, this is the L1. So this is L1. So Zi means the Z is starting from the Pictidius plane AB. But from there the clay layer 2 exists at a depth of L1. So at a depth of L1 by 2. Similarly, for layer 3, this is clay layer 3 at the middle. So you can easily know Zi is nothing but L1 plus L2 by 2. Similarly, at the middle of the clay layer means L1 plus L2 plus L3 by 2. This is how you need to calculate the Z, because this Z is essential to calculate the increase in effective stress delta sigma as a result of construction of the pile group. However, there are some specific cases are there in case of the pile group that we will try to understand. So these equations are remain same. I don't talk about all these things. This is in clay. This part I have already discussed. So you need to assume a Pictidius plane at a depth of 2/3 of L from the bottom of the pile cap. And for remaining depth is, since 2/3 is already gone, so that is L3rd, so 1/3 of the L, so that is remaining, or from the bottom of the pile tip, the incremental stress starts developing from a depth of L by 3 above the pile tip. Now, often you may encounter different situations in reality. So therefore you need to understand where to take the location of the Pictidius footing. So this is one of the important things. Now I have assumed a case 1 where the soil is homogeneous and the soil up to the pile cap is a strong strata. So in this case, the location of the Pictidius footing is assumed at a depth of 2/3 of L from the pile tip. Okay, but the load dispersal is remains same, that is 2 vertical to 1 horizontal. Now let us assume another case where a certain length of the pile, here it is L1. This L1 length of the pile is passing through weak soil layer. Now here, what do you mean by the weak? Weak means this soil layer L1 doesn't develop any kind of the skin friction or doesn't cause any kind of the skin friction. So it is simply ignored. The layer L1 is simply ignored. Now suppose say the L2 layer within which the piles are got embedded. So the L2 length only develops the skin friction. Now in this case, where shall I assume my location of the pictidious footing? So in this case, we should assume again at 2/3 of L2, 2/3 of L2 of layer L2, of layer L2, of layer L2. Okay, I repeat again. Second case, where the piles are embedded such that the L1 length of the soil is very weak, where it will not develop any kind of the skin friction. So this layer of weak soil is completely ignored for all calculations. We only consider the pile length, that is L2, embedded in the hard strata. Only that strata is considered for the calculation of the consolidation settlement. So again, within the length or depth of L2, we assume the location of the pictidious footing at a depth of 2/3 of L2, 2/3 of L2. The last condition, so where until the pile tip the soil is very weak, until the pile tip the soil is very weak, where it doesn't contribute for any kind of the skin friction. Then in this case, where do you assume the location of the pictidious footing? So in this case, it is straightforward. It will be assumed right at the pile tip. It will be assumed right at the pile tip. Okay, so these are the three conditions that that normally in real life one can encounter. So I repeat again. So the case one, where the soil is relatively hard strata from right beneath the pile tip, where the skin friction develops throughout the length of the pile, that is L. So in this case, the location of the pictidious footing is assumed at 2/3 of L, right beneath the pile tip. In second case, where the pile is passing through two soil strata having a depth of L1 and L2, L1 and L2. The strata L1 is of weak soil layer, where it doesn't contribute for any kind of the skin friction. So and only the length L2 within which the pile is embedded contributes for the skin friction. So therefore only the layer L2 is accounted for the consolidation settlement calculations. So in this case, the location of the pictidious footing is assumed at a depth of 2/3 of L2 only. The L1 is completely ignored. Now here in this case, when I say L1 is ignored, we can also assume that though this is a weaker soil, the piles are standing in the air. Piles are standing in the air. The third case, where the entire length of the piles are embedded or constructed in the weak soil layer. Here also we can assume that the piles are standing in the air. So, but the pile tip is resting on the firm stratum. So, in this case, the location of the pictidious footing is assumed right at the pile tip. So, I will stop it here only. This is what all about pile group capacity. We did discuss about how to calculate the pile group capacity and how to calculate the pile group settlement. So if anybody willing to ask a question, you are most welcome. Otherwise, we can go for the tutorial. Anybody has any question? Any question, please? So if you don't have any question, so please note down this sum. I think I have already noted down this sum. So please open. So I request everyone, so please open. Hello.
Yes, sir.
Yeah. So please, can you take out pen, paper, calculator? So let me talk to one by one. Vemulu Maunika. So since beginning of this semester, I could hardly speak to her. I think she is simply logging into foundation engineering and she goes away. So she doesn't want to listen to my lecture at all. Okay, PS. Vadapalli Kalyan. Madhukar Shinde. Not available. Ratna Shaili.
Yes, sir.
Yeah. Yeah. So can you please, could you try to solve this sum?
Like I'm writing questions first.
Okay. So please. Tanusri. So logged in and went away. Satish Kumar. Shivam Kumar.
Yes, sir.
Yeah. Did you try to solve the problem? No. So I think most of you.
Yes, sir.
Yeah, why you people are running away? The moment I open this Microsoft Teams, people are running away. Oh my goodness. So this is your stand. Very pathetic. Sheikh Abdul Arshad. Sampath Rao Sweta.
Yes, sir. So by using the formula Q ultimate is equal to AP, for finding load, we can use AP into Q dash and Q star, sir. And 0.5 PA NQ star tan phi dash, sir. By using the formula. First one and second one, for finding that we have K sigma not tan delta dash.
Yeah. Okay. Okay. Yeah. Please go ahead.
Yes, sir. I'm finding, sir. I'm calculating the values now, sir.
Yeah. Good.
I've
Good.
just found the formulas. Okay, sir.
Just open your handout because I have already forwarded the handout. Everything is available in the handout.
Yes, sir. I'm calculating now, sir. I've just seeing the formulas. I'm calculating now, sir.
Yeah, very good. Very good. Please,
Okay,
please.
sir.
Sagar Singh Rathod.
Yes, sir.
Yeah. So you also want to run away?
No, no, sir.
Yeah.
I'm
Your friends.
trying, sir.
Your
I'm
friends are
saying
running away.
yes, sir.
So no problem. If you want to run away, just run away. No issue. Where do you go? Vinay Kumar.
Yes.
Yes. Yes, boy. Ah, you are audible. You are audible, my dear.
Sir.
Yeah, yeah. Keshar Vani.
Yes, sir.
Ah, yeah. So are you solving the problem?
Yes, sir. I am solving. Sir.
Very good. Banu Prakash. So busy with something else. Muhammad. Rajafid
Yes, sir.
Muhammad.
Yes, sir.
Yeah. Are you
Sir,
solving
sir,
the
I'm
problem?
trying. Sir, actually, I'm a bit confused, like because of like a lot of classes. So, but my friends are helping me, like roommate and all. I'm asking them for like how to go with it. So
Yeah.
I'm trying. Sir.
Okay. What is the confusion? What is the problem?
No, sir. Actually, like because of this, sir. In general, my connectivity is very low. So most of the classes, I don't even get the slide, like the preview of the slides. So,
Oh.
sir, I have consulted the book that you have suggested. And
Mhm.
my friends also, they help me to do.
Okay. Okay. Good. 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 Yeah, I understand your situation. Please, please.
Yes.
Yes, Sivadarshan. So I think he logged in and ran away. Priyansh Kumar Nigam.
Yes, sir.
Yeah. So are you trying to solve the problem?
Yes, sir. Using the given formulas, I'm trying to solve.
Okay, okay. So try to open your handout also, so that I shared with you all.
Yes, sir.
So all the equations are available.
Yes, sir.
Prakash Sutar. Partha Sharma.
Yes, sir. I'm working on it.
Okay. Could anybody tell me what is the one important point that need to be taken into account when you solve this sum?
Sir, maybe we have to check for Q ultimate that this should not means Q dash should not be greater than Q ultimate.
Exactly. So your when you calculate the point bearing capacity, so as the Mayer of theory states that, so it will linearly increase up to a depth of L by D critical. So thereafter it becomes a constant. Here you can see in this slide, QP is equivalent to QL after approximately L by D is becoming the critical. So that can be taken approximately again 15 to 20 times of D. Okay, so this is the answer. Okay, so first let us try to solve. So the equation for computing the QP, point bearing resistance, is AP into Q dash into NQ star, and this should be less than or equal to QL. This should be less than or equal to QL, but that shall be decided based on the another parameter, that is LB by D critical. LB by D critical. So first calculate the product of AP into Q dash into NQ star. What is the value of NQ star?
56.7.
How do you pick up this NQ star value? So here this tabular form has been given. So this table is for a given soil friction angle of pi, you should pick up the value of NQ star. So here the pi given is 30 degree. So corresponding to 30, the value of NQ star is 56.7. So 56.7. So rest all parameters, in fact it is given in the sum also, or you can alternatively pick up from this table. Okay, so in the exam either this table will be given or the value of NQ star will be given directly. Okay, so NQ star is 56.7. Now Q means this is effective overburden pressure. Q means gamma times of D. Gamma times of D. So gamma of the soil is 16.8. Length of the pile is 20 meter. The length of the pile is 20 meter. Unit weight is 16.8. So what you will get is Q dash is equal to 16.8 into 20. So 336 kilonewton per square meter. AP means, so this is 360 by 360 in cross section. So this is a square pile. Square pile. So AP is 0.36 multiplied by 0.36, 0.1296. Q dash is gamma times of length. Gamma is 16.8, length is 20 meter, so 336. NQ star is 56.7, picked up from the table corresponding to internal friction angle of 30. So substitute in the equation of QP, that is AP, Q dash and NQ dash, what you get is 2469 kilonewton. However, this value shall be less than capital QL. Capital QL. So that means additionally you need to calculate the QL. So the equation for QL is 0.5 into AP into PA into NQ star into tan delta. NQ star into tan delta. Now 0.5 is anyhow numerical value. AP we have already calculated, that is 0.36 multiplied by 0.36, 0.1296. PA is atmospheric pressure, so this value is constant, that is 100 kilopascals. And NQ star already we have picked up, corresponding to angle of internal friction of 30 degree, that is 56.7. Then additional parameter is tan pi. So pi is given as 30 degree. So everything is known. Everything is known. Substitute straight away in the Q limiting equation. QL is nothing but 0.5 into 0.1296, that is AP into 100 into 56.7 into tan 30. So what you will get is 212.13 kilonewton. Now since we need to restrict to QP to less than QL, so QL can be taken as the final value of QP. So QL is less than QP, so therefore point bearing resistance is nothing but the limiting value of the QL, that is 212.13 kilonewton. So this is one of the important steps that you need to follow when you try to use the Meyerhof theory for the calculation of end bearing capacity. End bearing capacity. So this is simple and straightforward. Two equations are known. You need to pick up the parameters from the given table and straight away substitution, and you will get the point bearing resistance. Shall I go to next slide?
Yes, sir.
Now the next step is, how do you determine the skin friction capacity using the Meyerhof theory? So just refer to the handout that was given to you. The equation for skin friction QS is P into summation of tan delta. So this product of 0.8 multiplied by pi is referred to as delta. So where delta is soil pile friction angle, soil pile friction angle, multiplied by sigma V dash into Ki into Li. So this is the equation to calculate the skin friction capacity by the Meyerhof theory. Meyerhof theory. Now Meyerhof also put a one restriction very similar to the point bearing resistance, that the skin friction, average skin friction, increases linearly up to certain depth, and thereafter it becomes constant. Thereafter it becomes a constant. So therefore the very first step is, so until what depth the average unit skin friction is varying, and behind that it is becoming the constant. So the Meyerhof also given some kind of a guideline that the average unit skin friction varies until a depth of 15 to 20 times of d. So 15 to 20 times of d. So this is 15 d. So here in this case we have taken the variable depth of friction as 15 times of d. 15 times of d. So 15d, 15 into d, diameter of the pile, that is 0.36, 5.4. So meaning thereby, out of the total length of pile, that is 20 meter, the unit skin friction varies up to a depth of 5.4 meter, and for the remaining 14.6 meter depth, it is constant. It is constant. Okay. So this is the very fundamental thing. You must exercise the moment the problem is given by the Meyerhof theory. Meyerhof theory. Next, calculate the perimeter, that is P. Since this is a square pile, 4 times of 0.36, so 1.44. So then earth pressure coefficient, I think it is given already in the sum. earth pressure coefficient, determining the frictional resistance QS if K is 1.3, delta is 0.85, both are given. So K is given already, K is 1.3, so we don't need to bother. Then 0.8 times of 5, that is 0.8 into 30, 24 degree. 24 degree. Now another important step is how do you calculate the average increase in stress? Average increase in stress. So here the increase in stress is again calculated up to a depth of 15 times of D, 5.4. 5.4. So, or you can also alternatively calculate layer wise. But this increase in effective stress become a constant, the sigma v dash constant at 15 times of D, then thereafter it is constant. So you take the area up to 5.4 or up to a depth of 15 times of D. What is the sigma v dash? Sigma v dash, that is density multiplied by depth. Density is 16.8 multiplied by depth 5.4. So what you get is 90.72. 90.72. Now here there are we can, based on this variability, we can consider two layers. So until the effective overburden stress is increasing to a depth of 5.4 meter and behind 5.4 meter. So accordingly, so if you look at the equation, sigma v dash is varying and length is varying. So therefore these two can be taken as variable parameters. Remaining like perimeter is constant, tan delta is constant, and K is constant. K is constant. So it is taken for first layer at a depth of 15 times of D. QS is 90.72. So it is becoming as a sorry, for layer 1. Sorry. There is a small mistake here. In fact, you can take 3 number of layers. So the average they have not taken. In fact, you should take for 3 number of layers instead of the 2 number of layers which are shown here. So there is just something wrong.
Sir, why? Sir, I think it's correct now.
Yes, sir. Why 3 layers?
Sigma v dash is average, na. So up to first layer, it is 0 plus 90.72 by 2.
Sir,
That is
no, sir. They have given the average value of the entire layer 90.7.
Oh, sorry. Sorry. Yeah, correct. Sorry. So here it is 0 and here it is 90.72. Average is 0 plus 90.72 by 2, 45.36. So 45.36 for a depth of 0.54 meter and constant 90.72 for remaining 14.6 meter. Then this is how you need to calculate the QS. Okay. So one important thing that you need to remember is in the equations, for example, in Meyerhof theory, your sigma v dash is average value. But if you go for beta method or lambda method, the same sigma is, rather it is not average, it is mean. So these are the few important things you need to remember. Can I go to the next slide? you. The last step is how do you determine the overall pile capacity? So which is summation of QP plus QS. Our allowable pile capacity is nothing but ultimate divided by the factor of safety. Allowable pile capacity is nothing but ultimate divided by the factor of safety. So overall is summation of QP plus QS, that is 212.13 plus 1308, 1520.13 kilometer. So given factor of safety is 4. So Q allowable is 1520.13 divided by 4. So this is 380 kilometer. 380 kilometer. So though the ultimate bearing capacity of the pile is 1520 kilonewton, but we should allow the load increment up to 380 kilonewton only. So this is essentially because the pile is safe, not undergoing by excessive settlement. So when you apply the load of 380 kilonewton, your settlements are within the permissible limit. So if we exceed this load, then you may encounter excessive settlement. And when you reach 1520, either the pile may fail or the soil may fail. Anything could happen. Yeah, so note down the another sum. Consider a 15 meter long concrete pile with a cross section of 0.45 meter by 0.45 meter, fully embedded in sand. For the sand, given unit weight gamma is equal to 17 kilonewton per cubic meter and soil friction angle pi dash is 35 degree. Estimate the ultimate point QP with each of the following method: Meyerhof, Vesic, the method of Coyle and Castello, and based on the results of parts A, B and C, adopt a value for QP. Similarly, the above problem is related to the pile capacity in the sand, and the below problem is related to pile capacity in clay. Consider a pipe pile having an outside diameter of 406 millimeter. The embedded length of the pile is layered saturated clay is 30 meter, and the values of Cu are given for depth wise. From 0 to 5 meter it is 30 kilopascal, 5 to 10 meter it is 30 kilopascals again, then 10 to 30 meter, so it is 100 kilopascals. The groundwater table is located at a depth of 5 meter from the ground surface. Estimate QP by using Meyerhof method and Vesic method. So first note down the sum.
Sir, we have another class from 11:45.
Okay. No
Yes,
problem.
sir.
11:45. So which class we have?
Sir, wastewater
WW.
management.
WW. Okay, fine, no problem. So we will meet again at 5 o'clock. Okay, so try to solve by that time this sum, so then we can go for some more tutorial in the evening time.